Hello and welcome to the channel. Today we're going to be talking about why we have harmonics in music theory. You may have seen a chart similar to this one where you have these different positions of the harmonics with the fundamental note and then the overtones, and we'll be discussing why that happens. Here's an overview of what we're talking about. So music and physics. So the first thing that we need to discuss is standing waves, and that has to do with how musical instruments are physically shaped. The second item we need to talk about is log frequencies versus semitones and how audio frequencies map between semitones and back to frequencies. And the third item we will need to talk about is, now that we've determined what the frequencies should be based on physics, we will actually look at some measurements of a real song and try to find peaks. And finally, we will talk about future work and other difficulties with stuff that I have difficulty with. The first three, I will admit I understand very well. The fourth one I have some trouble with. But hey, we'll learn together. I'll make another video for future work, possibly, once I find some answers. The first item to talk about is, and this is my violin, instruments. Now, I'm going to show this to you on the violin, but it doesn't have to be a violin. It can be a saxophone or a flute. It can be any pitched instrument. So here we go. And by the way, if you haven't seen these before, this is a violin pickup. It's cool because you can plug it into a PA. Anyway, so the string has a length to it and a thickness to it, and you can pluck it. So what makes a violin make sound, you might ask, or for that matter, a flute make sound, or anything really? What you have is the string has to have vibrations to it, and these vibrations are caused by standing waves, which brings us to our first topic, standing waves. So what's up? When we have either a string, we can draw a string. Let's just say here's the bridge, here's the scroll. I'll just use approximate symbols here, and this is a string. Or for that matter, we have a flute or some pipe instrument, some wind instrument. Okay, either way, what you will see inside is the same. You can have the string vibrate like this, or it can basically the string goes up and down like this, or it can vibrate like this, where the top of the string goes up and down. And I'll draw the second half too. And the bottom of the string goes up and down, and this is supposed to be halfway through. Or you can have higher modes of vibration, where this piece goes up and down, this piece goes up and down, this piece goes up and down, and these are the nodes. These are the points on the string where the string stays in one place. But the same thing can happen inside a wind instrument too. So inside a wind instrument, you blow into one end, and you have pressure waves inside there. So you have air molecules that are moving back and forth, and you can have the air be still here and here, and all this air move back and forth. That's equivalent to our first mode of vibration, where all the air in the middle is vibrating. Or we can have the second mode, where the air molecules over here are staying still, and that's this one right here. And then the air molecules here vibrate and here vibrate, but here they stay still, and so on. You can have these. So why do you need these? Well, from a practical standpoint, let's look at a video. So I went into my garage and I mounted a camera on top of my car, and I tried just playing this game with a rope. You can see, I can pause the video, you can see it is right now all the way down, and now it's all the way up, and so on. That's kind of what that is. We'll just fast forward a little bit, and then I'm trying to move the rope faster, but the reflections, because when the energy goes from me over here, here's my shoe, the energy of the wave goes here, and then it bounces off the attachment point on the other end, and it's reflected, and that's the reflected wave is fighting back with me with how I'm playing with this rope. But eventually the rope goes into a somewhat stable situation. So if we fast forward a little more, you can see it's kind of the rope. Well, I'm still fighting with the reflected waves here, still trying to figure out the speed. But like here, it's close. So here you can see that the node is approximately here, even though I'm doing a bad job at the rope. But here we have the down, and here we have the up. And the same thing, here we have the up, and here we have the down. And I'm not doing the rope thing perfectly here, but I tried different things there. You can see the middle is kind of staying as a node. And here I tried going faster, so the nodes would be about here and here. So there are 3 of these lobes. See, the middle one is down, the side ones are up, and so on. So the point of this exercise is to say that when you try to shake the rope at a rate that it doesn't want, at a frequency that it doesn't want to be shaken at, then the reflected waves will interfere. And physically, the way we draw that is, well, first of all, we draw a line and we can draw a wave. So what happens is when the wave reflects, it depends on what kind of medium it reflects, but let's just suppose there's one kind where it will have a phase flip, and there's another case where it won't have a phase flip. But in this case, we will have a phase flip because the wave reflects of a medium that is more rigid than the rope itself. So like this is more a higher index of refraction, if you will, except you don't have refraction here. But what you have is when you have a wave that comes here and it ends right here, well, the reflected wave, so normally it would have been going up and then down, so normally, except there's this block here which prevents it from going down here. So instead it will go here, but instead of going down, it has a phase flip. Phase just means talking about this or this, sometimes denoted using the Greek letter phi or phi. And so you have, instead of going down, the wave goes back up. So it goes up, and so the reflected wave is the same, and then it reflects here and goes back up again, and reflects here and goes back up again. So the reflections are helping the driver of the wave. Okay, so then what you have is, you can also have integer multiples of that. And by the way, the wavelength is twice of what this is. So this is only, this length over here is L over 2 if L is the wavelength. So there's 2 of these because a full wave is going to be up, down, and back up again. So this is a full wave. This is L. Okay? And then we can fit a full wave, so we can take whatever frequency this is and times it by 2. So we can have like this, and like this. And then when that reflects, it'll go back down because of the phase flip, and it'll go like this, like this, like this. And then that reflects and it goes back up like this, like this, like this. So the reflections are all helping us. So therefore, we have this as a stable node. And then what we can have is, what if it's not an integer? It's like, well, okay, because these are staining waves. These are integer multiples of the fundamental resonant frequency of this chamber or string or pipe or whatever. Now, what if we went, suppose we went like this, and like this, okay? So the wave hits the other end at this point, which it's not going to with a rope because the rope is tied there, but okay. Let's just say if it did inside of a, if it did, then the reflection will involve because this is, remember, this is a rigid medium, so there's going to be a phase flip. So it flips the phase here instead, and it goes here and here. That's how it travels back. It travels there on this side and travels back on this side. So physically, if this were to happen, then the result will be that we will add them together, and this one and this one, they will cancel each other out, so we have a straight line as a result. This does not happen due to destructive interference, because when two waves are in interference, I'm introducing this term here. If we have, say, this wave, and we have another wave like this, and we add them together, we'll have an even taller wave, because they are both up at the same time and both down at the same time. Kind of drew this bad, but so they help each other. They constructively interfere with each other. But if you add two waves together that are like this, and one that's like this, one is up, one is down at the same time, and the result, physically, they will add together and you'll have no wave, or you'll have less wave depending on which one is stronger. So they're kind of playing tug of war here about who's going to overpower whom. And so here, if you have waves that are not integer multiples, that are not standing waves, if you had them, then they would interfere with each other. And this is where we come back to this situation with, maybe not here, but in some parts of the video I was fighting with the rope, and the reflections would fight back with me. And so that's what happens when you try to oscillate, try to vibrate something at a frequency that it does not want to vibrate at. It's these the reflections in this chamber, they interfere with each other, and as a result you do not have constructive interference, and therefore you need a standing wave, which means that any resonance, any sound, in the case of musical instruments, coming back to this chart, any sound you have must be a multiple, we'll call it lowercase n, times f naught. So f naught is the 0. We usually say, you know, f naught, that's how you spell it, f naught, and then we have n. So this is integer multiples of the fundamental frequency, where the fundamental frequency is the lowest frequency that we can have coming out of this instrument. And that's what we will have. You might be familiar, on a string instrument, you put your fingers down. So A. I don't know if I'm in tune here. Okay, here. That's B, A, B, B sharp, C. So that's what you do on a violin. But on a flute or something, you would have something similar. It's just you would be pushing buttons or covering holes. So on a violin, when you put a finger down, what it does is it makes the string shorter. So therefore, where you have this resonant frequency situation, if the string is a little bit shorter, then the wavelength has to be shorter, which means that the frequency has to be higher. So that will make it so that you have a different note that you're playing. And that's a violin, but on a flute or something, or another instrument, when you push a button or cover a hole, that's the same thing that you're doing. You're basically making the pipe shorter, or you're making the pipe longer. I don't know which one is. I think it's shorter. You change the frequency that comes out of the string or pipe. Alright, so we covered why we need standing waves and why we need integer multiples or whole number multiples of f naught, the fundamental frequency. The next item to cover is log frequencies and semitones. And we need to predict where the harmonics will fall. First of all, let's look at this chart right here. This is from this random website, Music Dictionary. In this chart we have this big octave C, and then the small octave C, and the small octave G, and then the first octave C, first octave E, and so on. You have these different notes, G, B flat. You have these different notes. So that is a question, like how do we know that these are the overtones? These are harmonics that instruments produce. But how do we know? How can we show mathematically that this is what must happen? And what we can do is we have the Wikipedia. So they actually, on Wikipedia, they give you the equations here. You search for piano key frequencies, the frequency for a note number n, and they're using piano key numbers instead of MIDI numbers. I like to use MIDI numbers, but regardless, it just changes one number in there. And then this is a note number as a function of frequency. But if, suppose we didn't have this, we only have this picture, and we know that this is A4, scientific note name is A4 of this note right here. It is 440 Hertz. Oh, wait, so, okay, that's neat. You mouse over, it shows you, okay. Yeah, so the way I got to this one is I just clicked on this picture. That brings it up here. And you can zoom in to make it bigger. So what you do is, you need to count how many semitones. And for those who don't know, semitones are half steps. So like one semitone up from this A is this B flat. And 2 semitones from the A is this B, 3 semitones is C. So you can count half steps are the same as semitones. You just need to remember to count all the keys, not just the white keys. And then you can count down from the semitones too. And then we would use positive numbers to say we're going up, negative numbers to say we're going down from that note. So let's put this into an equation. The other thing that we know, by the way, is when you go an octave higher, so say not this octave, but this other octave, this other A, it's 880. See, 880 Hertz, 440 Hertz. If we go an octave lower, it's 220 Hertz, 110 Hertz, let's see, 55 Hertz, and 27.5 Hertz, okay? So we know that each octave gives us a either doubles if we're going up, or cuts the frequency in half if we're going down. And then the other thing is we need to make sure we remember how many semitones there are in one octave. So we'll start at this C. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we came to this next C. We counted 12 semitones. So that is important. And we can write that. We can take the note. We can do n minus 49, n minus 69, whichever you prefer. So this n is the key number. This n is the MIDI number. It just depends on how you, and this is an arrow, by the way. It's a horribly drawn arrow, and so is this. Or we can just say delta n. Delta n, that represents how many semitones away from A440, or A4. Semitones from A4. A4 is the scientific note name of that piano note, or just any note. This works with any instrument because every instrument has a pitch. We find it convenient to use piano keyboards to point out where the notes are, but this applies to any pitched instrument. So we count how many there are, and we remember that when we go up an octave, it doubles. So we need to use powers. So it's 2 raised to the delta n, except delta n is in semitones and the 2's octave thing is in octaves. So we need to divide by semitones per octave. So divided by 12. So 2 raised to the power of delta n divided by 12. And then that we need to multiply by 440 Hertz times that. So 440, because we know that if we go 0 steps, 0 semitones away from that A4, then this exponent will be 0, and 2 to the 0th power is 1. Anything to the 0th power is 1. Times 440 is 440, and that gives us the frequency of that A. Now, if we're 1 octave above, or 12 semitones above, then 12 over 12 is 1, and then 2 to the 1 is 2. 2 times 440 is 880, which is the correct answer. So that is equal to the frequency. So there we have it, and then we can go back to the Wikipedia page and see to make sure that we have this right. So n minus whatever note you're starting with as the 440. Yeah, so delta n over 12, 2 to that power times 440 Hertz. So that is correct. We just derived that equation, okay. So what this allows us to do is to calculate the frequency based on the note number. And then we need to go backwards too. So let's just do some algebra. We divide both sides by 440. By 440 hertz to be specific. You need to keep the units in there so that the hertz cancel, the 440 cancel, and F over, and I'll flip sides too. I'll put this on this side. So F over 440 hertz equals 2 to the delta n over 12. And then, well, we need to get rid of, we need this delta n, that's what we want. So let's take log 2 of both sides, log 2, so then we have log 2, and on this side, by the way, the log 2 and the 2 to the cancel. These two cancel, so the log 2 stays on the left, obviously. F over 440 hertz equals delta n over 12. Okay, and the final step is to multiply both sides by 12. And then this over 12 and times 12 cancel, and I'll put the delta n on this side again. Delta n equals 12 times log 2 f over 440 hertz. And so that's it, I guess. Okay, there we go. So delta n tells us how many semitones we are above the A4 key. And if we go back to the Wikipedia page, we can see that n equals 12 times log 2 f over, okay, yeah, over 440 hertz. And they add the 49, and with the regular n, we don't add anything, and we just do delta n, or just whatever, just how many semitones above that A key. And we arrive at the same answer. Okay, so if that is the case, and just as a reminder, f equals 440 hertz times 2 to the delta n over 12. Okay, these are two equations that are important to remember. So what you have is you have a way to translate between essentially note pitches and physical frequencies. Well, okay, where will the harmonics be? We go back. Let us review this for just a moment. We learned that we have destructive interference if we don't have integer multiples. We have constructive interference if we have integer multiples. So therefore NF0 is the harmonic. And n is any number. It will be a sum of everything, actually. The signal is going to be equal to, and this is a time signal, we take the sum over n. So n equals 1 until the number of harmonics, and then we have some amplitude that is specific to n multiplied by e to the I 2 pi f sub n times time, where f sub n is equal to n times f0. So that is mathematical. Just if you'd rather not look at that, don't look at that. But basically what the frequencies, what the harmonics will be is f equals f0 times n, or n times f0, whichever way you prefer to write it. And what you have also is, what we want to know is what are the note numbers for the harmonics. And I just realized that I'm using this lowercase n for two things here. On this page I'm using it for some integer multiple. On this page I'm using n for the note number. So let's just say, I'll just keep it as delta n. Let's just allow f0 to be 440 hertz. Just for the example, f0 can be anything depending on which piano key you're looking at or which note you're looking at. But let's just set it to 440. We're trying to find the harmonics of the A4 note. So what are the harmonics of the A4 notes? Well, okay, we can find that they will be f equals, it can be some integer multiple of f0. So therefore we have some integer multiple times 440 hertz. So it could be, you know, we could say there's, you know, 1 times f0, 2 times f0, 3 times f0, and so on. In frequencies, you know, in hertz, we have 440 hertz, 880 hertz, 1320 hertz, I think. I'll have to check if I'm right on that, and so on. Okay, well, what are the harmonics in note numbers? So what are the harmonics in note numbers instead of frequencies in hertz? And the answer is, well, we take these and we use these equations on them. So in this case, we want this equation, 12 times log base 2 of the frequency divided by, okay. So the thing is, in our case, we are doing the frequency over 440, which is to say 1f over f naught, and actually the f will be f naught in our case, 2 f naught over f naught, and so on. So really we just have 1, 2, 3, and so on. In this case, I specifically chose to set f naught to be 440 because we have this division by 440 over here, so we divide 440 by 440 and we have just 1, and then 880 by 440 and we have just 2. So I specifically chose that just for the demonstration, but this math works anywhere. It doesn't matter what specific note you're talking about. The harmonics will be the same for any note. So you have basically 12 times log 2 of 1, 12 times log 2 of 2, 12 times log 2 of 3, and so on. Okay, we can calculate these. You just have to go to Google, and then you go, okay, so of 1 would be 0. Okay, 12 times log 2 of 2 is 12. Okay, interesting. This is where we're coming to some interesting space here. Log 2 of 3 is 19.01, about 19. So we'll write about 19. 4 is going to be exactly 24, actually. So then we write 24. And then we replace this 4 with 5. 27.86, and then 6, 31.01. So we can do 31.01. So around 31. So where do we expect the harmonics? We expect them at 0, 12, 19, 24, 28, 31, and some other notes. Okay, so that's what we expect. Let's go back to the keyboard and try to find where these are. Let's just say we start with this C right here, and these are these numbers that we found. They are in semitones. So really, we were finding the harmonics for this A440, but the math, you can do the math for homework if you want. But basically, if you put F equals, this 32.7 hertz instead of 440 hertz, you will arrive at the same conclusion. It's just all your notes will be shifted by however many semitones this is. You'll just have like this. Let's see, the note value here is 69 for this note, so it'll be, and the notice here is 24 for 45. So you'll have negative 45 for this first one, then you'll have negative 33, I believe, 12 above that for this next one. So you'll have the same spacings between notes, but it's just the absolute value will be shifted if you start with something that's not 440. So, okay, we start here. So this is 0. The next one is 12. So the first harmonic will be on this C, and then the next one will be 12 semitones above that. 1, 2, 3, 4. I won't even count. It's 1 octave above. Okay, so then this one will be the first overtone, second harmonic, first overtone. So this C octave above that, right? Okay, the next one is 19. So we go back here, 19. So if this is 12, then 13, 14, 15, 16, 17, 18, 19. This G, right? Okay, then we go back. It's like, okay, next one is 24, which is 24. Okay, 20, 21, 22, 23, 24. So the next overtone will be here on this C, 24, 25, 26, 27, 28. So then this E will come next. 29, 30, 31. This G will come next. And if we kept doing the math, we'll find that this B flat comes next. But obviously I just did the math till here. Now, let's look at this chart again. We have the C, we have a C an octave above, we have this G, we calculated that, we have this C again, then we have E, then we have G, then we have the B flat. And what did we say? These are exactly the numbers that we calculated. So this is how many steps, how many semitones rather, the harmonics will appear at. And music theory over here tells us that. So this is awesome. We can predict where the harmonics go. And just as a reminder of what we did to find this. So first, define F. Use F equals equation, EQN, to find your note of interest. So that's step one. And we used this equation, but in our case, I just set that to this number to 0. I'm like, let's just do the A4 note. But you can set it to any note you want. So we use this equation, and then step 2 is find whole number. Okay, and then this, by the way, step 1, this is your F naught of F naught, whole number multiples, right? So these are, 1 times F naught, 2 times F naught, 3 times F naught, and so on. And then 3, you finally have the, convert these frequencies. Convert these frequencies into note numbers using the delta n equals equation. And that is using this equation. So we plug in the frequencies that we found, 440, 880, whatever other frequencies you find, and that gives you this. And this gives you delta n, how many semitones away from the A4 it is, from the 440 hertz A. But you can shift it over to whatever octave you need it, whatever note you need it. And that's what we did. And then step 4 is count semitones on piano frequency chart to locate harmonics. And ta-da! And that's what we did. And so we found these numbers. This was the result of step 3, and step 4 was the part where we went to the chart here and we came up with the result here. Well, alright, so we used the log frequencies, we did the equations, and we counted semitones, and we predicted where the harmonics will be for any note. And now it is time to look at some experimental measurements. Alright, so over here I wrote a computer program. I can share it with you later, but it's got quite a few components. I don't have time to cover it here. But this is in Python. It's called 15freakplot.py, and then we have I'm going to invoke it here, but before I invoke it, I'm going to give it the Lindsay Phantom.mp3 audio file. I just wanted to show you what it sounds like before we start looking at it. So it has a little count off. About 4 seconds into it, we start the audio. We'll listen to about 1 minute of it. At about 50 seconds, 51 seconds is where the interesting part will come in. Okay, that's cool. So as I said, at about 51 seconds. Okay, so yeah, you heard it's a highly distorted electric guitar over there. That, heads up, it'll give us a little bit of trouble later. But the violin part is easy though. So what we do is up arrow, so we type Python, our script name, and then the reason I'm doing this instead of doing it through this console is because this is an IPython interactive console, and it'll mess with our GUI instantiation. So I'm actually doing a GUI in PyQt5 for this. So I hit enter. Okay, that's cool. So this is when I mouse over, it does these red lines right here are it does the first, let's see, the first 12. It predicts the Python program actually, and I can show you a little bit of the code, but just not a lot. So it calculates the transform, the blue lines, it does like, it takes the samples, the audio samples. So it'll take the window, it'll do some windowing actually. It uses the NumPy Blackman window, and it converts the notes that are in the note range that we want to frequencies, and then instantiates some time, and then -2 pi frequency time is the phase list. And then we take this and we shift it. So we shift it, we make that into a complex exponential. So SH is our shift factor, and then SP is our shifted product. So we have the samples, we multiply by the shift factor, and SW is the windowed samples that were windowed. So we multiply the samples by a window first, and by the shift. We can talk about windows later, but basically the multiplying it by a window makes the data look cleaner. So we do that, do the sum again, and then this SW is the one we end up using because it looks cleaner. Put it into LW, so we convert this to decibels. We take the absolute value, which will take the magnitude actually of this array, NumPy array, then we take the log 10, multiply that by 10, and that gives us decibels. That's LW. Okay, that's our LW variable, and then this is just generate note. Okay. But what we really do is we calculate the harmonics. Initialize, we calculate the harmonics in here. So what we do is we take this LW, okay, we just scale our things somewhat, and then what we really want to do, pay attention to, is we take this F0, we take the N0, which comes from, where does it come from? Oh yeah, it comes from the X data. So when we move the mouse, it looks at where the mouse is on the X-axis, and it'll set that to our 0th node that we want to look at. So then we have the N0, we convert that to F0, the frequency, and then we iterate over the number of harmonics that we want to cover. We define the multiplier as, because I will be 0 through whatever number exclusive, doesn't include the last number. So we add 1 to make this start from 1, and mult starts from 1 instead of 0. Then we take n mult times the F0. And this is the fundamental frequency. So that's the frequency, and then we convert the frequency back into a note number, freq to note, and then we set that to where the red line will go. And then just as a reminder, we have note to freq will have that equation for us, 440 times 2 to the, and then we're using MIDI note numbers here in this Python program, so we have -69, and then same thing here, +69. These are the equation that we covered, and then if we have an argv that we pass from it, then that's what we use as an audio file name. So that's what we're doing, and then I've been playing around with window size and whatever. Okay, so that's, I guess we didn't go into detail into the Python code, but that's basically what it does. Very simple. So when we move the mouse around, what it does is it plots the red lines are where, using the equations that we just used, these equations, and then these numbers that we found, these steps, that's what the Python program does. It finds these numbers for us. Based on where the mouse cursor is, it finds the harmonics for that note where the mouse cursor is. And so these are the numbers. Okay, and then if you take the mouse out, it'll just take it off the plot. And also in the legend, it shows us where the mouse cursor is, what the N naught is, what the fundamental pitch is. Okay, the other thing, the blue is Blackman windowed log intensity of the microphone, transformed into the frequency domain, of course, using log frequencies as well. So we hit the space bar and it plays us what it is. So I'm gonna hit the down arrow, we navigate. Okay, so this is, listen carefully, it's not just a violin. There's a violin in there, but there's also a keyboard in there. Either a piano or a keyboard, or a keyboard that sounds like a piano. So there are two instruments in there. And then when we use our little helpful tool, so the violin is actually here. And I wrote a Python program to be able to click on the plot, and it'll play back a tone at that frequency. So that is the tone that it generates at this frequency of note number 76. And this is the audio sample. Okay, so the violin is obviously here because we checked it with the tone. Tone, audio sample. Okay, and then we move this here back to about 64. The tone generator will actually round the note number for us. So it's okay that it's 64.1. It'll still play at 64. So that's the tone. Okay. You can hear that in the background. You can hear this note in the background. So there's a keyboard that's at this location, and then there is a violin at this location, and they are 1 octave apart. Maybe I should just take a screenshot. Okay, here we go. Take a screenshot, MS Paint. Okay, take a screenshot there. So now I can at least mouse over things. Maybe make this full screen. Oh, okay, I see. Okay. But anyway, so we have here, like, this is the fundamental frequency for the keyboard. This is the first overtone or second harmonic. This is the third harmonic, fourth, fifth, and so on. So you can see that there's peaks here at all these places. There are peaks at all these places. And then if we go back to, so we go back here, now we point this to where the violin is. Okay, so we take a screenshot, we paste that in here, and then we put this full screen. And what do we find? Well, maybe we don't want it full screen. And what you can see is this fundamental pitch, it covers all the harmonics, whereas this 1 octave above it will skip some of these that exist for the fundamental one. But the other thing is that I want you to notice, subjectively we can actually tell that it's 2 instruments, or at least 2 notes playing from 1 instrument, but in this case it's 2 instruments. They are 1 octave apart. You can tell because over here, you see, this is where the second instrument is, the violin is, and this is where the keyboard is. So for the keyboard one, you have all these harmonics, and every other one after this one is strong, and then it's weak, strong, quite weak, strong, very weak, strong, very weak. So at some point you start losing the strength of every other harmonic for this lower octave one. But for the higher octave one, you don't have peaks on half of the ones that the lower octave one has than the keyboard. So on the violin, you don't have those every other peak because you are playing an octave higher. That's just how the math works out. And whichever ones you have peaks on, the keyboard that's playing also has peaks on those locations. We saw that. And so, well, point number 1 really is the math. When we do this math of where the harmonics go, in particular that would be this function right here, we take a frequency, a fundamental frequency, we multiply by some integer multiplier that's positive, and then we convert that to a note number. We actually see, when we look at the blue I did not generate. The blue is just a Fourier transform, it's a frequency spectrum plot. So the blue is the actual data that we measured from the, in this case, Lindsay's studio or wherever she recorded this, from the microphone basically. Not my personal microphone, this is Lindsay's audio. But basically we predicted the peaks to be here, and the peaks are here. That is awesome. Like, we can use physics to predict music, which is great. And so that brings us to the end of our third point, which is to say that, oh, okay, so we have experimental measurements and we observe the instruments on our plot. We can actually use our predictions to find peaks and match peaks to the instruments. Okay, so far so good. So then what happens when we add a little distortion? So far we've looked at this clean audio, and we'll close these without saving. Clean audio, lots of peaks, we can match them up, we can predict them, whatever. So we're here, like, we can still match peaks some seconds later. Same thing here, peaks still match up. We'll just keep seeking. We're trying to seek to the 51-second position. Ah, 52. Okay, where did the peaks go? Let's play this sound for... That's the sound. If we go by ear, let's see. That's about right, actually. Let's see, about 57. Well, you can actually kind of see a peak there, sure. There are some peaks that line up, but it is so difficult to find. And then if we seek here, okay, so about 45 actually, 45. That's kind of about right. It could be an octave higher, but that might be about right. So we do see peaks there, so that's probably where the note is. But it's like, wait, so why is the peak here then? Yeah, so this is really confusing. So we have, like, we add this highly distorted electric guitar and we don't know what to do anymore. But that is part of future work. And then the other thing is, back when we were seeing peaks, even we were subjectively separating the instruments, we were able to tell that, oh, every other peak is much shorter, so therefore that must mean that there's a second instrument that is an octave higher. But some objective way would be nice to write a computer program that is able to separate different octaves, find instruments that are octaves apart. And then the conclusion, well, in conclusion, we are not able to do difficult stuff like this yet. Distortion is very not easy on us, but we are able to do, let's see, we are able to do easy stuff like this where there's peaks, and we are able to use science, you know, we're able to use these equations that we derived, and we also know that musical instruments require standing waves, which require the premises for which we set for ourselves in order to find the harmonics that we predicted. All right, well, thank you for tuning in. Let me know if this helped anyone, and I hope everyone has a nice day.